Section 3.2, Trigonometric Integrals. This is from OpenStax Calculus Volume 2. Of course, go to their website and download this for free if you would like to do that. There's the web address right there. Okay, so when it comes to integrals involving sines and cosines, the one rule of thumb to remember is we want to get a single sine or a single cosine. Okay, no squares, no cubes. We want to get a sine or just a cosine to the first in there somewhere. Now, sometimes that's easy enough and we can just use U substitution. Other times, however, we will have to use the Pythagorean identity, sine squared plus cosine squared equals 1, so that we can kind of formulate it so that it's going to have a single sine or single cosine. Alright, so example 12 here, evaluate cosine cubed sine x. Okay, easy enough, we've got a single sine. So we're going to make a choice of U equals cosine cubed, or actually just cosine. That way, when we take the derivative, du, we will get a negative sine x dx. So I'm going to write this. First, I need to rearrange my du. That'll make negative du equal sine x dx. Alright, so I'm going to have a negative sign in here, and that is u to the third. And sine x dx is actually going to replace this right here, so that's just du. I've already taken care of the negative sign, so now I can integrate this as negative u to the fourth over 4 plus c. But of course, u was cosine, so this is negative cosine to the fourth x over 4 plus c. So if we have a single sine or a single cosine, our job gets a whole lot easier. So now let's go ahead and look at number 13. We have sine to the fourth x cosine x dx. It's set up differently, so we'll go ahead, we will use u equals sine x. That way du is just a single cosine x dx. We don't have to adjust anything here, so we can write this integral as the integral of u to the fourth dx, or du, that's going to replace the cosine, which will be u to the fifth over 5 using our power rule plus c, and that is sine to the fifth x over 5 plus c. Now, I said at the beginning of this chapter, but in this chapter, techniques of integration, we want to make sure all of our steps are shown. Okay, we aren't going to leave anything out. Even though I've shown you how to use CoCalc, you can check your work with that. But ideally, every single step is going to be justified. And these are called techniques for a reason. We want to make sure that you can use those techniques. All right, next we have cosine squared x, sine cubed x. There is a problem here because we do not have a single sine or a single cosine. So I'm going to manipulate this just a little. I'm going to leave this as cosine squared x sine squared x times sine. Okay, now that doesn't seem like it helps, except that I can now rewrite this sine squared x. Sine squared x, I can make that 1 minus cosine squared x. Okay, and of course I have my sine x. Well, now I have a single sine. All right, so I can do the same trick from before. U equals cosine x, and du is negative sine x dx. Okay, adjusting that, that's negative du equals sine x dx. So rewriting this over here, that is the integral of u squared times 1 minus u squared du. Now I'll have to make sure I have a negative sign in there because I had to adjust my du. Alright, so I can then work with this. This is u cubed, nope, just u squared minus u to the fourth. I'm going to go ahead and make that a negative and a positive. And then once we use our power rule there, that is negative u cubed over 3 plus u to the fourth over 4 u to the 5th over 5. Sometimes I can't do arithmetic either. Haha, just sort of happens that way. Plus c. So I can now write that, plugging my u back in. That is negative cosine cubed x over 3 plus cosine to the 5th x over 5 plus c. So again, our trick is to try to get a single sine or a single cosine. Okay, number 15, do something very similar. With this, I've got a cosine cube, so I'm going to pull off 2 of those. Okay, so this is going to be cosine squared. Well, that's going to be 1 minus sine squared. So I'm just going to go ahead and write that. 1 minus sine squared x times cosine x sine squared x. Okay, now I have a single cosine, and I have actually all even powers of sine. Alright, so this, rewriting this, I'm going to distribute the sine this way. So that is a sine squared x minus sine to the 4th x, and all that's times cosine x dx. Okay, my u substitution at this point will be u equals sine x du is cosine x dx, so that this is the integral of u squared minus u to the 4th du. Alright, so using my power rule, u cubed over 3 minus u to the 5th over 5 plus c, which, substituting u back in, sine cubed x over 3 minus sine to the 5th x over 5 plus c. And you might notice some similarities between these two problems. One with sine, one with cosine. The sines is the only thing that's different. No pun intended. The positive and negativeness of each one of those is the only difference there. Okay. Now, so far, the good thing is we've had an odd power of sine or cosine somewhere. If we don't have that, okay, we have these next two. If we don't have that, we've actually got some formulas. They're called power-reducing formulas, or double angle identities, I believe is what they are called often. So we can use these. So if I want the integral of sine squared x, this happens to be equal to 1/2 minus 1/2, so the integral 1/2 minus 1/2 cosine 2x dx. I can just substitute that identity in for that, which will be, if I take the antiderivative of that, that'll be 1/2 x plus minus 1/4 sine of 2x plus c. That is all there is to it. So if you have only an even power, then that is a very useful tool to have. Okay, cosine squared x, same idea. We have this other identity. That is the integral of 1/2 plus 1/2 cosine 2x dx, which will be 1/2 x plus 1/4 sine 2x. And no dx, we just need a plus c in there. We have taken our antiderivative. Okay, that'll come in handy. Now, there's a flow chart coming up next. Okay, a problem-solving strategy. I suggest you read this, but we've actually been using this the entire time. If we have even exponents, we use that identity, sine squared x equals that, cosine squared x equals that. Okay, so if they're both even, you can use that. If one of them is odd, then you pull off a power there. That way you get that single sine or that single cosine, and then use the Pythagorean identity. Okay, so keep that in mind. Alright, so let's look at this one. Alright, so we have got an even cosine and an odd sine. Okay, so I'm going to actually use two things here. First, I'm going to pull off a single sine. Alright, so this will be the integral of cosine to the 8x, sine to the 4th x, sine x dx. Now I'm going to use my Pythagorean identity on this one right here. So that will be the integral of cosine to the 8x, 1 minus cosine squared x squared, since that is to the 4th power. And then we have our sine x dx. Alright, doing a little bit of algebra. Actually, we'll go ahead and do our u substitution. That will make this easier. Cosine x for u, since we have our lone sine over there. That way we get negative sine x dx, or negative du is sine x. Okay. We want that lone sine, or that cosine, the one that's by itself, we want that to be our du. So choosing the other one makes a lot of sense. Okay, so this will be negative integral of u to the 8 times 1 minus u squared squared du. Now, multiplying that out, we get negative integral of u to the 8 times 1 minus 2u squared plus u to the 4th du, which is negative integral of u to the 8 minus 2 u squared, no, to the 10, add those exponents, plus u to the 12. Okay, applying our power rule here. In fact, I'll go ahead and distribute that as well. Negative u to the 9 over 9 plus 2u to the 11 over 11 minus u to the 13 over 13 plus c. And substituting back in, that is negative cosine to the 9x over 9 plus 2/11 cosine to the 11x minus cosine to the 13x over 13 plus c. Okay, 12 to 13. Okay, good. Just double checking my work. I always like to do that. Okay, and triple. Okay, number 19. Evaluate sine to the 4th x dx. Okay, there's no way I'm going to get a single cosine out of this. So what I'm going to have to do is actually use my double angle identity first. So this is going to be the integral of sine squared x squared, which, using that sine squared is that 1/2 minus 1/2 cosine of 2x. This is 1/2 minus cosine 1/2 cosine 2x. Now that is squared. Okay, double distributing there. It's going to be 1/4 minus 1/2 cosine 2x plus 1/4 cosine squared 2x. Okay, now we still have a cosine squared, so I'm actually going to apply that again. Bring all this over. Most of this is going to come down. 1/2 cosine 2x plus 1/4. We will substitute that in there. Okay, and cosine squared 2x, okay, is going to be 1/2 plus 1/2 cosine 4x. Okay, there that is dx. Alright, distributing here, we get 1/8 plus 1/8 cosine 4x minus 1/2 So 2x 1/4. Now we still have to integrate this. Alright, so this will be, we'll actually combine these two together. That is going to be 3/8. Okay, minus 1/4 sine 2x. Okay, plus 1/32 sine 4x plus c. Alright, and that is it. Have to keep a lot of these options open. Okay, some different things, some different strategies we can use. Alright, the next thing we have got here is cosine cubed x. Alright, we can get a single cosine out of this by making this cosine squared x times cosine x, and then convert that cosine squared into a 1 minus sine squared x. Alright, so u can be sine x, du will then be cosine x dx. So this is the integral of 1 minus u squared du. Alright, that'll be u minus u cubed over 3 plus c, which, plugging our u's back in now that we have taken the antiderivative, that is sine x minus sine cubed x over 3 plus c. Okay, notice we only have a cosine squared in this next one. So we will first use our double angle. This becomes 1/2 plus 1/2 cosine 6x dx, which is 1/2 x plus 1/12 sine 6x plus c. Okay, fair enough. All we have to do is apply that double angle identity to this, and we can take the antiderivative fairly easily. Okay, now we have three formulas here that are a rule, okay, if you have different angles and things. Okay, so we're going to do just a couple of these, but this definitely will come up. So we just need to see which of these apply and then use them. So first, we've got a sine and a cosine, and the sine, the a is 5, and the b, and the cosine is 3. Okay, so we have a sine times cosine, so that is going to be this second one right here. So this is going to be the integral of 1/2 sine of a minus b, so that'll be 2x, plus 1/2 sine of a plus b of 8x dx, which will be 1/4, negative 1/4, because we have cosine of 2x, minus 1/16 cosine 8x plus c. Okay, so figure out which formula applies if you have different angles, and then, well, use it. Next we have cosine 6x, cosine 5x. So that is going to be the third on that list. So this is the integral of 1/2 cosine a minus b. Well, a is 6 and b is 5. This is the cosine of x plus 1/2 cosine of 11x dx. So this will be 1/2 cosine, no, 1/2 sine x plus 1/22 sine of 11x plus c. Alright, now we're going to turn our attention now to secants and tangents, because previously we said we want to get a single sine or a single cosine. Well, because of the way that secant and tangent are related, okay, we really have two options we're going to try to look for. One, if we can get a single secant squared, that will be very helpful. Okay, a single secant squared, or if we can get a secant and a tangent. Okay, so there's again a problem-solving strategy on maybe another page. Yep, the next page. But, you know, for now, that's kind of what we want to look for. Okay, well, looking at number 24, because we have a tangent there and an odd number of secants, my first thought is going to be to make this equal to the integral of secant to the fourth x, secant x, tangent x. All right, so that way I can make u equal to secant, and du is then secant x, tangent x, dx. So then this is the integral of u to the fourth du. All of that is taken up with du. So that's u to the fifth over 5 plus c, which is then secant to the fifth x over 5 plus c. And we do also have a Pythagorean identity that we can use, and that is, I'll go ahead and write this up here, secant squared x equals tangent squared x plus 1. Okay, now you can rearrange that to be tangent squared x equals 1 minus secant squared x. Occasionally that will be useful if we have an even number of either one. We can kind of convert between the two of them. Okay, next we have got tangent to the fifth and secant squared. All right, so what we are going to do, again, we want a secant or a tangent alone. We either want a secant, a tangent, or a tangent or a secant squared. So here we have secant squared. So I'm going to go ahead and actually just use a u substitution of tan x, and then du is secant squared x dx, and this becomes u to the fifth du. So u to the sixth over 6 plus u, which is tangent to the sixth x over 6 plus c. Okay, and here's our problem-solving strategy, and I suggest that you read that, see if it makes sense to you. If it does, use it as much as you can. Okay, I'm going to continue going. I'm really going to use those strategies as I go. Okay, so keep that in mind. Alright, so I have a tangent to the sixth, secant to the fourth. It seems to me I have a pair of fourths, or a pair of twos here, so I'm going to rewrite this as the integral of tangent to the sixth x, secant squared x, times secant squared x. Okay, so one of those is going to become a 1 plus tangent squared. 1 plus tangent squared x, secant squared x. Okay. The benefit there is that I am now going to be able to have everything in tangents, okay, and the secant squared is going to be my du. Okay, so go ahead and make u equal to my tangent, du equal to secant squared x dx. And this will be the integral of u to the sixth. Well, that's going to end up being, well, u to the sixth. And that will be a u to the 8 du, which will be u to the 7 over 7 plus u to the 9 over 9 plus c, subbing in tangent, tangent 7x over 7, tangent 9 to the 9x over 9 plus c. Okay, next we have tangent to the fifth, secant cubed. Okay, so the first thing I'm going to do is go ahead and pull off, because both of these are odd. Okay, I have a to the fifth and to the third. I'm going to take a secant and a tangent off. So this will be tangent to the fourth x, secant squared x, times secant tangent. So it'd be nice if all of this were in terms of secant, because this is the derivative of secant. So let's go ahead and do that. That'd be 1 minus secant squared x squared times secant squared x, secant x tangent x dx. Okay, so we actually had something like this earlier. This would be, if I work this out, if I make u equal to secant du equal to secant tangent dx, then I've got 1 minus u squared times u squared. Okay, so working that entirely, that is going to be a u squared minus, squared. That's be a minus 2u squared, so minus 2u to the 4th, plus a u to the 6. Okay, du. So we have u cubed over 3 minus u to the 5th, that'll be 2/5, plus u to the 7 over 7 plus c. Subbing that back in, we've got secant cubed x over 3 minus 2/5 secant to the 5th x plus secant to the 7th x over 7 plus c. Okay, good. Okay, next we have tangent cubed x. Again, it's odd, so I'm going to make this into the integral of tangent squared x times tangent x. Pull one off. Let's go ahead and turn that tangent squared into 1 plus alright, now that should be actually a 1 minus, or a secant squared x minus 1. I need to erase that whole thing. Secant squared x minus 1 times tangent x dx. Okay, now this will be integral of tangent x secant squared x minus tangent x dx. Now the integral of tangent is natural log absolute value of secant x. Right, and for tangent, we're going to do a u substitution, the tan secant squared. U will be tangent. Du will be secant squared x dx. And this becomes the integral of u du. So we get u squared over 2. So that our integral is tangent squared x over 2 minus natural log of the absolute value of secant x plus c. Now I'm going to have to go back here because I actually made an algebraic mistake back here. Well, it's the Pythagorean identity. I'm going to go back to 27 real quick. Well, that one is complete. This actually should have been secant squared x minus 1. Okay, this should have been secant squared x minus 1. Fortunately, that just makes this 1, or u squared minus 1 squared, which actually produces the same thing. So we're just fine, no big deal there. Fixed it. Okay. Now that we've got 28 under our belt, we can look at this next one. We have secant cubed x. Okay, this is a serious integral to look at. Okay, so don't be too ashamed to go back and look at it again. Okay, this one has a different technique to it. It doesn't seem like it'd be that strange, but it is. Okay, so what we're actually going to end up doing is writing this as secant squared x secant x. Okay, what we are going to do is do integration by parts. Okay, I'm going to take u and dv. My u is going to be secant x, and my dv is going to be secant squared x, because that's easy to integrate, whereas secant is easy to differentiate. So that will be secant x tangent x, and the integral of tangent, or secant squared, is tangent x. So we are going to get secant x tangent x minus the integral of secant x tangent squared x. Okay, now if we make a substitution like we've done already, we'll leave our secant x, but tangent squared is going to be secant squared x minus 1. This may not seem immediately obvious why we're doing this. Integral of secant cubed x, I'm going to go ahead and split this up, plus the integral of secant x dx. Okay, now the reasoning here is because this is cyclic. Because we have the same integral on both sides. We've got this on both sides. So we're going to add secant cubed x dx to both sides. So this is going to be 2 integral of secant cubed x dx is secant x tan x, plus, and the integral of secant is ln natural log of secant x plus tangent x, okay, plus c. So this leaves us with the integral of secant cubed x dx is secant x tangent x, 1/2 of that dividing by 2 on both sides, plus 1/2 natural log the absolute value of secant x plus tangent x plus c. And from this point forward, we're going to take this to be a rule. If this shows up in any other problems, we are going to say we happen to know what that is, and we're just going to use that. Right, number 30, tangent cubed x secant to the 7th x. All right, this seems like a place we are going to end up using one of our identities. Let's go ahead and take a tangent squared off of that. Tangent cubed. Tangent squared x times tangent times secant to the 7th x. Okay, so let's go ahead and actually we're going to pull off a secant. We're going to pull a secant off of that as well. So this will be tangent squared x, secant to the 6th x, and a secant x tangent x. Converting that tangent squared into one, make sure I get it right this time, secant squared x minus 1. Okay, secant to the 6th x, secant x tangent x dx. Alright, this becomes, there's our du, so our u is going to be secant x, and our du will then be secant x tangent x dx. So this is going to be, I'm going to go ahead and use my u substitution here. This will be u to the 8 minus u to the 6 du. That will be u to the 9 over 9 minus u to the 7 over 7 plus c. And secant to the 9th over 9 minus secant to the 7 over 7 plus c. Okay, the last thing we're going to use is something called a power reduction formula. Okay, and this applies to secant and tangent. They're actually, we already had the reduction formulas for sine and cosine if we have squares of those. But if we have secant and tangent, we have these formulas. Okay. All right. So we've already said that we're going to take this as a rule, but the way this formula reads is if the exponent there is just a secant, a plain old secant. Okay. Well, n equals 3 for us, okay, because we have it to the third power. So this is going to be equal to 1 over n minus 2, or n minus 1, which would be 2, secant, and then we'll subtract 2 from that, so that is secant to the first times tangent, plus n minus 2, that would be 1, because our n is 3, n minus 1, so that is 2, so 1/2, integral of secant, we'll take that down 2, so that's just secant x dx. Well, we happen to know the integral of secant is natural log of secant x plus tangent x. And there is what we derived earlier. That was a whole lot quicker than the way we derived it earlier. But using integration by parts sometimes does come in handy, so we have to be able to do it and be prepared to do it. Okay, tangent to the fourth, we're going to use this. Our n is 4. This is going to be equal to 1/3 tangent to the 3x minus the integral of tangent to the 2x dx. These actually come from our integration by parts formulas. Okay, now let's go and apply this, but now n equals 2. Okay, so 1/3 tan cubed x minus, gonna hold on to that, tan squared is going to become 1 over 2 minus 1, which is 1, tangent to the 1x, minus the integral of tangent to the 0x dx, which is just x. So we end up with 1/3 tangent cubed x minus tangent squared plus x. Let's see, because this is just 1, and there it is. Last one in this one, and we're going to actually stop this one quicker. Alright, so we'll use our formula. So n is 5, which makes this 1/4 secant to the 3x tan x plus n minus 2, so that's 3 over n minus 1, which is 4, integral of secant cubed x dx. Now we're going to just call it because that is, we know what secant cubed is, so we could continue, but we are going to call that problem complete. Alright, that is the end of our trigonometric integrals section. Whew.